Pleasant morning, everyone. Today, we will present our review on ground subsidence mapping and monitoring in major metropolitan areas in the Philippines using InSAR and GNSS technologies. Ground subsidence refers to the gradual sinking of the Earth's surface. It can occur naturally when such water dissolves subsurfaces, limestone, and forms sinkholes, or due to human activities, including excessive groundwater extraction, rapid urbanization, and land reclamation. This phenomenon is particularly concerning for coastal megacities. In the Philippines, did you know about 60% of the population lives in coastal zones, making subsidence a serious threat to urban infrastructure, flood risk, and land stability. Monitoring subsidence is therefore crucial to ensure sustainable urban planning and disaster risk mitigation.
The objectives of our review were to provide accurate and consistent information on subsidence across major Philippine metropolitan areas, identify areas that are sinking, quantify the rates, and examine correlations with human activities and land use, establish a baseline dataset to guide planners and policymakers in addressing infrastructure and flooding risk, analyze patterns, similarities, and difference in ground deformation across different cities based on existing studies. This study used a secondary data analysis approach. We primarily relied on the work of Sulapas et al., which measured subsidence from 2014 to 2020 using InSAR and GNSS techniques in Metro Manila, Metro Cebu, Metro Davao, Metro Iloilo, and Legazpi City. We also compared these findings with other published studies for validation and broader interpretation. The analysis involved 3 steps: extraction of subsidence values and spatial patterns, including rates of sinking, deformation shapes, and geologic context. Comparative evaluation, checking for consistencies and differences between studies to account for variations in satellites, observation periods, or human activity changes. Interpretive synthesis, combining all findings to identify patterns, hotspots, and potential causes of subsidence. Remember, it is important to note that this study relied solely on published data and did not include new field surveys, InSAR processing, or numerical modeling.
Today, I will summarize the findings by metropolitan area. The Metro Manila showed extreme subsidence in parts of Bulacan with rates up to 109 mm per year. Areas along Marikina Valley Fault sank at 2 to 42 mm per year, demonstrating the influence of both human activities and tectonic processes. Areas like Camanava and Las Piñas showed improved conditions after groundwater regulation, highlighting the effectiveness of management interventions. However, Metro Cebu experienced high localized subsidence, particularly in Barangay Pangdan, Naga City, at about 106 mm per year, largely due to quarrying. Borders areas sank at around 11 mm per year. Subsidence in reclaimed zones showed nonlinear behavior, emphasizing the complexity of ground deformation influenced by natural and human factors. Metro Davao experienced moderate but consistent subsidence, with Panabo City reaching 38 mm per year. Urban expansion, aquaculture ponds, and soft river plain sediments contributed to ongoing and ground sinking. Metro Iloilo had moderate rates of 2.6 to 9 mm per year, particularly in districts with rapid development on deltaic sediments. Even moderate subsidence is significant due to Iloilo's low-lying coastal topography. Legazpi City had subsidence rate of 7 to 8 mm per year, with maximum localized rates up to 29 mm per year. Volcanic deposits from Mayon volcano, soft soils, and groundwater extraction collectively influence subsidence.
The synthesis shows that subsidence is widespread across Philippine metropolitan areas, driven by both natural conditions and human activities. High-risk zones include Bulacan, Camanava, Naga City, and parts of Davao. Importantly, areas where groundwater management was implemented show measurable improvements, demonstrating that mitigation strategies are effective. In conclusion, ground subsidence in major Philippine metropolitan areas remains a pressing geohazard. Soft sediments, reclaimed lands, and intensive groundwater use contribute to the highest sinking rates. Continuous monitoring using InSAR and GNSS, combined with responsible groundwater management and sustainable urban planning, is essential to mitigate risks of flooding, infrastructure damage, and long-term land instability.